on this computer. Okay, it should be recording now. Can you guys see the little recording thing on the side? Cool. Awesome. So yeah, as I mentioned, we need to know these axioms just in general, but also we need to pay extra attention to few things. Just in general, you need to know closure. And I'm sure most of you guys already know this. So if it's some material you've seen before, sorry about that, but I'm just going over everything for everyone. Closure under addition, and second closure under. And these multiplication and addition can be defined in whatever way they're defined for the vector space. They're not necessarily always going to be, if you have a vector AB plus CD, it does not always have to be that that's equal to A plus C, B plus D. That's not always the case. So it depends on how the addition is defined for your vector space. Kicking into some vector space / vector space axiom questions. I know these are a lot of questions over here. I won't go over through all of them, but I did want to bring this up because I think it'd be helpful for your midterm. Before people ask, I haven't brought any questions from the midterm or anything like that. Like I've only prepared like what I think would be the most helpful for you guys. So yeah, first of all, I want to give everyone like a second to think about each of the questions before I just jump into the solution. So we're going to start with this one. I'll label it as 1 and I'll create a new page so I can write on it. But first, I want people to think about whether this is or isn't a vector space. You're welcome to share your answer in the chat. I will ask later on that we give everyone a chance first, but because this is the first question, just give it a thought whether you think this is or isn't a vector space, and perhaps give your answer in the chat for why it may or may not be. This is good.
Is it okay to give a hint?
Let's just give, okay. You can give a hint. Yeah, go ahead.
Okay, think about closure. Think about closure.
Yeah, so like we mentioned, these are the properties that we need to pay extra attention to. Is addition and scalar multiplication usual ones? What do you mean by that? Not a vector space, okay.
No. They can be any operation you want. So even though it's addition, just think of it just as some operation. It doesn't have to be like the usual add things together. It can literally be anything that obeys the axioms.
Yeah, that's true. But just in this question, I think it's better if I specify it to like the addition and multiplication being as normal real numbers, just because otherwise you won't be able to disprove or prove using the axioms. Right?
Oh, they're talking about that set. Yeah. It's just it's just the regular addition operation on the real numbers, or R2.
R2. Perfect. Yeah. So we got a few yeses in the beginning, but I think the answer is shifting to a no now. And in fact, it is no. Could someone tell me perhaps why? Which axiom or property does it fail? I see someone said scalar multiplication. Perfect. Because the scalar, when we do scalar multiplication, like C multiplied by, let's say, XY up, and we were going to say this is a part of C. I shouldn't have used C then. Let's use, I don't know, D as our scalar, where D is a, let's write this over here. D is a part of real numbers. D could be negative, right? So if D is negative, D multiplied by XY would not be a part of C. So not closed under. Perfect. So that's that question there. Any questions about that before I move on to a few of these follow-up questions I have over here? Can I scroll down for sure? I don't have anything written here just yet, but I will in a minute.
I have a question about this question.
Yeah, go ahead.
So if you're asked this question on the exam, how would you like to prove it, like with the best way?
Yeah, so good question. So I'll write it a little bit neater just for this question. So I'll say a claim not a vector space, and then I'll say doesn't hold property of closure under scalar multiplication, and then because, and then I'll show the stuff I wrote up over here. I'll just bring that down there. Does that make sense? I thought closure
Okay.
was for subspaces. No, that's a good question. I know in my tutorial as well, people got very confused about that. So just to clarify that, like you need closure under addition and multiplication to hold for vector spaces too. It's not an axiom. It's not a thing that we need to like, you know, something that we write like this. It's not written there, but it is for both of them. In fact, like you need closure under addition and multiplication for both subspaces and vector spaces. That's a good question though.
Okay. But how to prove if it's not under closure of multiplication? Because I just can't see the proof.
You give a counterexample. So basically you show an example of where it's not closed under scalar multiplication. So you try to find a scalar such that when you multiply the vector by the scalar, it's not in the set anymore. So usually when you come across the type of question that goes, oh, is this you know, is this or is this not a thing? Usually what you want to do first is you want to try some examples, right? So if you're not sure, try some examples, see if you can get it to, see if you can find an axiom that doesn't hold. If you're convinced, if you've tried like some examples and they all seem to be working, then probably you're probably good to try proving it.
Okay, thank you.
Yeah,
Thank
and
you.
in the chat, Nicholas as well gave us a good example, counterexample there too. So yeah, that's a good solution. Yeah, perfect. So let's move on from that to question number 2. Now, the reason I brought this question up here, and I'm only going to take up 2 or 3 of these properties as per what people would want. But the reason I brought this one up here was because I think it will be helpful for you in your midterm if you're given, you know, a vector space question. You're able to now know these. So all these properties over here are true. Okay, I'll go over 2 of them, which I think will be the most beneficial for you. And you're able to now know how to prove that, and then you're able to use that in your midterm, should you need it for any vector space questions. So I'll actually start with A. And so I'll write this down here. V is a vector space, and you're given U, V, W are part of big V. Now we want to prove that U plus V equals U plus W, then V equals W. Okay, I'll give everyone a second to think about this. And out of curiosity, does anyone know what this property is called? Additive inverse? Not quite, not quite. Another guess? Oh, perfect. It is the cancellation law. I'll write this down here as well. Cancellation law. Perfect. Good that people know that. Okay, so think about how we can prove that, and then I'll jump into the proof, how we can do that. Subtract U on both sides. Is that strong enough? No, that's not strong enough. Unfortunately not. Otherwise it'd be too easy. We need to make use of the vector space properties. And perfect, Austin said it there, and I know someone said it above as well. We use the additive inverse property. So we're going to use axiom 4, I believe it is, which is, so we know, I'll write this up. There exists an additive inverse U, let's say minus U, so it's a part of V. Then what we can say is U plus V is equal to U plus W. We can change that into minus V U. We can add minus U to both sides. And that will equal to minus U plus U plus W. And then we're going to use another axiom here.
No, you don't need to know the name of the axioms or the number of the axioms. You just need to know like what they are. I don't think he's going to ask you for the names or what the numbers are.
Yeah, but it would be helpful to know that this means the additive inverse. And like right now, we're going to make use of another property, which is commutativity. And I would, just to be safe, write it in the exam in case it is a part of the mark scheme. But I'm saying, like, you don't need to know the number for sure. But what you do need to know generally is that, like, you know how you've done this in your assignments? Commutativity. I think it would be helpful.
That's associativity, not commutativity.
That's a good point. Associativity. Clearly, I haven't parsed up on my own definitions. Perfect. So then we're gonna carry on again, and we're going to do a little bit more splitting up. I'm just gonna write this step. You don't need to do this step, but just so it's a little bit clearer, this is the same thing as this plus v, and that's the same thing as u plus. Just I've written that because I'll show you in a second, because the definition of additive inverse generally has that form, in the fact that we like to write this in the form. So I've just brought it to the same form down here, but you could have skipped the step here. Then we know that this is equal to 0 plus v and is equal to 0 plus w. And we know by another axiom, which one is it? Axiom, which one is it?
Yeah, Elder Josh, that's because subtraction isn't really an operation. The only operations are scalar multiplication and vector addition. So it doesn't make sense to say subtract u from both sides, because that's not really a thing. Subtraction is really just adding the additive inverse. Very pedantic, but you'll be expected to be very pedantic with these proofs and write out every step.
Perfect. So that's part A. Does anyone have any questions about that? I'm going to be a little bit mindful of time. I don't want to spend too much on vector spaces, but another one I did want to highlight to you guys was property E. You know that 0 multiplied by any vector is equal to 0. Well, we know that, right? We know that when you multiply 0 by any vector, it should be equal to 0. But how do we prove that? Like if you're asked to prove that in the exam, how would you prove that? And in fact, you're going to make use of what we proved in part A. And you'll see why though. So proof. And the way you would do that is, we know 0 is a part of real numbers, right? And 0 is a part of the vector space. These are just like given things that you should already know this of a vector space. Now, for v a part of the vector space, what must hold true? Well, we're going to say 0 multiplied by v should be equal to 0 plus 0 multiplied by v. This is true. This is trivially true. And then because of the multiplicative axiom, we can say this is the same thing as 0v plus 0v. Now, another thing we know about 0v is that 0 multiplied by v, because of axiom 3, I believe it is, 0 plus v, sorry, this is the same thing as 0 plus 0v, right? We're saying 0v is equal to this, and it's equal to this. So we're saying that as a result of both of these equations, 0v plus 0v is equal to 0 plus 0v. And now we're going to make use of the cancellation law we proved in part A. Zero v equals to 0. That's it. Does that make sense for everyone? Okay, I'll take the silence as a yes. Subspaces, similar thing. Not really, but we need to know the three things, right? The 0 needs to be part of the vector space, and sorry, a part of the subspace, and closure under addition and multiplication. I'll ask you a question. I asked this in my tutorial before. Do we really need this axiom, this property, sorry? And if yes or no, why not? Could I go off for a minute? Of course. You can take a screenshot of the whole page. We need this property. Okay. It has to be non-empty. Sure, yep. Non-empty. But another thing, the 0 vector. Yes, if there's 0, it's not a vector space. No, you're right. Because you can prove without proving others. What I wanted to make the point was, this is used to just prove non-emptiness. The 0 vector can actually be gotten from property number 3, because 0 multiplied by 0 is still a scalar, right? And 0 multiplied by any u, a part of where u, a part of big U, would also give you 0. So like you can get that from there as well. But yeah, that's all I wanted to say there. Those are subspaces. I'll give you guys a little bit of time on these two things here. Determine if it's a subspace. I know I've introduced a new definition here that you've not seen before, orthogonal, but like this is completely fair game to be asked in the exam, in the sense that if you're defining a definition whether or not you knew it before, if they defined it for you in the question, it's fair game to use that and ask you a follow-up question based on that. So take a second to think about these two and whether they would be or wouldn't be subspaces. First one, do people think this is a subspace or not? We know whether U isn't there in the first place. Is there a situation that a subset is non-empty but it doesn't contain a zero vector in it? No, zero vector must always be in every subspace. Okay, the first and second questions here. First one, do people think it's a subspace? No, perfect. And that's whenever you're thinking first thing, yeah, perfect. The first thing you should always be thinking, would zero be a part of it? We see that zero would not be a part of S2 because if we have, because if x1 equals x2 equals x3 equals 0, x1 minus 4 x2 plus 5 x3 equals 2 doesn't. Okay, how about the second one? It is not. Would you mind scrolling right a bit? Oh, of course. I'm talking about this question over here for now. I'll get to that question in a second, the harder one over there, but I'm just talking about the question here for now. But I will zoom out for a bit. Yeah. No, all good. So question 2, is it a subspace or not? What do you guys think? No. Why not? Which of the 3 properties fail? Zero vector, perfect. So again, using the same trick as before, we're gonna say, let's check first property, is 0 a part of W? And in fact, we're gonna see that the 0, we're talking about 2 by 2 matrices, so we're talking about 0 in this case is equal to 0, 0, 0, 0. And if we do, and do we know what transpose is? That might be something you don't know. You don't know identity matrix. My bad. You haven't covered this part, so you don't.
Transpose just means you take the matrix and you interchange the rows with the columns.
Yeah. I just don't want to confuse people, but and yeah, that's all you have to do. Just switch the rows. So I'll just tell you that 0 transpose is also just equal to 0, 0, 0. And if you haven't covered matrix multiplication, this won't make sense either. But 0 transpose multiplied by 0 will just be the 0, 0, 0, 0. I don't want to confuse people right before the midterm though, but this will just equal 0. And that's not equal to the identity, which is 1, 1, 1. Or, sorry. Perfect. I may have missed it, but where's the recording? Will this recording be posted anywhere? We will try to share it from our AMAX, I think, YouTube channel. You'll see it on our socials. But I will try the prof to like post it on the Quirkus page as well, or the Piazza, but I'll have to ask Parker about that as well. Slides are the same. Yeah.
Quick question.
Yeah.
Yeah, sorry. A quick question is an identity matrix equal like the same as an elementary matrix? Are they like the same interchangeably?
Identity matrix just means, you don't need to know this, but identity matrix just means on all the diagonals you have a 1.
Okay.
And
yeah, I know that, but like there's also like another term like the elementary matrix, which is kind of similar. Is that like the same thing?
I'd say so, yeah. No, elementary matrices. Oh, not too sure. I don't think so. No, elementary matrices are ones that you can use on row operations. Those are not the same thing. Elementary matrices are something like if you needed to interchange the first, so if you had 1, 2, 3, 4, and you needed to do and you wanted to, so if you're doing RREF steps and you're trying to switch the first and second row and you're trying to do like R1 switch with R2, well, we know that's going to be 3, 4, 1, 2, but the elementary matrix is a matrix that you can multiply by this to get this. So that would be, in that case, 0, 1, 1, 0.
Okay, thank you.
But yeah, don't confuse yourself too much with this because it's not something you directly need to know.
Right, okay, thanks. Thank you.
Okay. With that being said, I'll take the second question to the next page, and I'll give everyone a second to think about that. Let me just take a screenshot. This part. What does it mean by orthogonal matrix? It was defined up here. Again, don't confuse yourself too much. You don't need to know that before the midterm. Here's the second question. Give it a second to think about it, and then I'll take it up.
Just to remind everybody about their first semester logic, whenever you're asked to prove an if and only if statement, that means you treat it as two separate statements and you prove the first direction and then you flip the statement around, prove the second direction.
Perfect. So let's start off by taking this up. Like Alex said, we need to, when we have an if and only if statement, we have something like this. And to prove it, you need to prove the forwards direction. I like to write it like that. And then later on, we're going to prove the backwards direction as well. And what I mean by this is, for the forward direction, we're going to prove first if L is a subspace of R2, then B is equal to 0. Okay, so let's start with that one first. To prove this way, I'm going to do it a little bit differently. I'm going to use the fact that the original statement is equivalent to the contrapositive. And so this is the same thing as saying, same as if B does not equal to 0, then L is not a subspace of R2. Okay, if we're saying that, I'll just drop this off for now. I'll come back to that. Is not a subspace of R2. So how are we going to start by proving this? Well, first of all, let's say, okay, in order to show, let's say we are assuming this, right? So now we need to check if L is a subspace of R2. If it is a subspace, it has to contain the 0, 0 vector, right? Or the 0 element. Exactly, perfect. So we're going to check if it contains it, and then let's see if B equals to 0. When we plug 0, 0 into there, we see that 0 is equal to M times 0. So plug, let me write this over here. We are going to plug in 0, 0 as 0, 0 has to be a part of L for it to be a subspace, right? And then when we do plug in 0, 0, we get 0 is equal to mx, m multiplied by 0 plus b. So we get b is equal to 0, which is a contradiction with which contradicts with so we have a contradiction with b does not equal to 0, hence L is not a subspace of R2. So that's that direction, and that's all we have to do there. Any questions about that direction? Cool, cool. Now we need to do the other direction. So we're now going to write this as this way. And this one, yeah, was there a point there? No? Okay. Yeah, I don't know. Someone sent their CA48 assignment in the chat. I don't know what's going on. But
I'm going to delete that if that's okay.
yeah, of course, of course.
Yeah.
I'm sure there is a way to do that directly as well, but we just did it using contrapositive there. Now we're gonna say if b is equal to 0, then
Also, yeah, that could have been a direct proof. I mean, as Kathleen says, there's more than one way to skin a mathematical cat. So if you wanted to do this as direct proof, you could. I don't know how I don't know how harder it would be as a direct proof, but I know you could probably do it as a direct proof.
what is wrong with b equals to 0? Nothing's wrong with b equal to 0. It's just in this direction, we were assuming that b does not equal to 0 to start off with. And if we are seeing that b is equal to 0, then that's a contradiction. Why are we plugging in 0, 0? Because we are plugging in because you need 0, 0 to be part of L for it to be a subspace. That's the 0 element, I guess, in that case. Awesome. Next part, the other direction, we need to, if b is equal to 0, then L is a subspace. So we know that 0, 0 is a part of L, right? If it isn't, if it wasn't, sorry, it wouldn't, I mean, 0, 0, what am I trying to say here? Sorry, so yeah, because if b is equal to 0, then y is equal to mx plus b is equal to mx, just mx, and if 0 is equal to m multiplied by 0 is equal to 0. So that part holds true. Now we are going to, so we know that part is true. Now we need to suppose,
Why does it contradict the original statement? It contradicts the original statement because we assume that b is not equal to 0, but then we showed b equals 0. So that's a contradiction. Because we're showing if b is not equal to 0, then it's not a subspace. Well, we assume it's a subspace. And then, well, yeah, okay. I mean, like if it's, yeah, I mean, it's like a contraposition, but I mean, part of it's using, like, I guess, contradiction.
Yep. And then here so for the first part, we showed that if we first showed that it is 0 is a part of the.
Yeah, it's a mix of both.
And now we need to show closure under addition. So we've taken two elements, A and B, Y2, and we're going to show that the addition of those two will be a part of L. So we need to show, now we're going to do x1, y1, I'll write it like this, x2, y2, and that's the same thing as, if we're saying addition is defined as it, because we're working with r squared, so addition is going to be like this, x2, y1 plus y2, and that when we put into L, we see that, well, that's the same thing as saying y1 plus y2 is equal to m multiplied by x1 plus x2 plus b plus b, but b is just equal to 0, so that's just the same thing as x1 plus x2, which is the same thing as mx1 plus mx2, and that part's fine. So we are saying that, therefore, so we are saying, which is still a part of L. Sorry, I should have included that. So we are able to conclude, therefore, I'll write it like this, therefore, x1 plus x2, y1 plus y2 is a part of L. Now for the second part, for closure under multiplication, multiplication, I've butchered the spelling. We're gonna say let C be a part of reals, and we need to show C multiplied by x1, y1 is equal to C x1, C y1 is a part of L. So let's check if it's a part of L. Well, C of y1 would equal to C of sorry, M multiplied by C of x1, C of x1, and that's the same thing as saying C multiplied by M of x1, and it is being recorded, yeah, and then we are able to conclude that this is also a part of L, because again, B was equal to 0, so sorry, I should write that part as well. So that's B, which is the same thing as M CX1, and that's the same thing as C M of x1, sorry, C multiplied by M, and then M multiplied by C of x1, which is L. So we've shown closure under multiplication as well. Any questions about this general? I'll put the whole question up so we can take a screenshot if wanted. Can we just
Can we do addition and scaling in one step to save time? It's best, at least at this point in the course, to show all the details. The TAs will be very picky about that. I can say from experience. So just to be on the safe side, you should, at least at this point in the course, show all the details.
Okay, another question about the details. Hello?
Yeah, go ahead.
Oh yeah, sorry, just thinking if you
No,
hear
all good, all good, all good.
So about this type of like equation that you've proved in, like I think we all seen that like the way that you've written this like is correct, but is there any ways that even with this type of wording or this type of proof, any marks will be lost? I don't think so, just curious.
I mean, like if I was writing in the exam, you should be a little bit more like explain a little bit more. Like for example, here I should have said like this equality because assuming, like I'm just writing the answer just so you guys can understand, but like in general, like give a lot more details that whatever I'm saying out loud, I should be writing down as well, because assuming B is equal to 0 and stuff like that, like just to be safe, like I would write a lot more, but will this recording be uploaded on your YouTube channel? That's the plan. That's the plan, yeah.
Okay, thank you.
No problem. Cool. Before we go into a break, I want to do linear.
I have a question, sorry.
Of course.
So about like for the part over here.
Mhm.
So like the part where the y plus 1 plus equal plus y2,
Mhm.
why is there only a singular b? Shouldn't it be like 2b or something, since you're supposed to add like the both equations together? Shouldn't there be like two, like y1 plus y2 equals m bracket x1 plus x2 close bracket plus 2b or something, since you're adding the two equations together?
You are right. You could also have written this as let's say y1 is equal to m x1 plus b, and then written y2 is equal to m x2 plus b, and I think that's better actually. So thank you for pointing that out. Let's say b1 and b2 again. So and then adding these two together, you would get y1 plus y2. Well, just the b's just go away, right? So I think I've been a bit lazy there, but that's the whole point with that one. Yeah, that's a good point though. M of x2. So, but you just we get rid of the b's eventually anyway, right? But yeah, that's a good point.
Okay, thank you.
No problem. Okay. Linear independence. We know what linear independence means. Some of us may not, but just in general, linear independence, whenever we're talking about this, there's a few things we need to remember. And the main point is this one here, right? Like whenever we need to prove linear independence, we need that whenever we equate the coefficients of so if we write a linear combination of those vectors, the coefficients must always equal and equated to 0, sorry. Then those coefficients must always equal to 0. And yeah, I guess I just wrote here as well, the empty list is declared to be a linear independent set. I'll ask you two quick questions regarding this. There wasn't really something too hard I could find for this one. Before we jump off into a quick break, let's talk about this one first. Give it a second to think and tell me if this is true or false, I guess. Start off with true. I see a lot of trues.
Can anyone tell us why it's true? because it's trivial.
I think as it contains the zero vectors, so a ways to form zero vectors, whatever are the coefficients to zero or anything else, as long like there is a coefficient combined with the zero vector, it can be like 3 or 5, but it still have the formation is still be zero. So actually it's not linear dependent. Oh, it's not a linear. Oh, sorry. I think it's linear independent. My bad.
So are you arguing it is linearly dependent or independent?
It's dependent actually.
Perfect. That's good. That's good. Let's see what people in the chat are saying here. 1 multiplied by 0 is 0. That's true. We're going to make use of that in a second. So to prove this, it's not that complicated, so I'll just write it here. It is in fact true. And the reason it is true is, let's say, let 0 be the, I guess, the 0 vector. And let's say v1 all the way to vk are other vectors in the set. Then we're going to say we have a non-trivial linear combination, which is going to be one, let's say, let's just say 0, like a1 plus a2 v2, sorry, v1 plus all the way to ak, sorry, it'll be ak plus 1. Actually, no, it'll be a1, a2. Let me just say a0 here, and then a1 here, and ak.
Non-trivial means that like they're not all the AIs aren't 0.
Yeah, and so the reason it's non-trivial here is we'll see that we can put any real number here, and even if, let's say, let a1 equals to all the way to ak is equal to 0, a0, let's say, and a0 equals to, let's say, 1. We know 1 multiplied by 0 is still 0, like someone said correctly in the chat before. So this whole thing would become 1 multiplied by 0 plus 0, because everything else, all the coefficients are 0 otherwise, is equal to 0. And this is true, right? 0 is equal to 0. But the reason this is linearly dependent is because we have a non-zero coefficient and non-zero coefficient. Hence, set is linearly dependent. That's it. Okay, I'll give everyone a little bit of time to think about the second one here. Upper triangular, I know this isn't something you've covered before, but what this means is matrices with the form that you have 0 here and non-zero elements directly above. Let me just say. Above the diagonal, they're non-zero. I know you don't know this now, you will know this later. How did you get a0 multiplied by 0 to a0 is equal to 1? No, I just said let a0 equal to 1. And you've seen that there exists one non-zero coefficient such that this holds, and that's enough to disprove it by counterexample. Okay, so I'll give you guys a second to think about the second one here, and then we'll jump into that. Is the main diagonal all 0 too? So it says it here actually later in the question, if all the diagonals are non-zero. So assume they're not. So if the diagonal entries of M are all non-zero, then prove all this stuff. And then we'll check if it holds, if they're non-zero as well. You're saying they're linearly independent? Okay, let's think about it. You are right. It would be linearly independent. But just how would we prove that? And I think this would be helpful for your midterm. This like kind of trick, like if you had a okay, yeah, you could use an example, but what example? Triangle matrix, like I said before, like e.g. Let me write this one properly. E.g. Let's say 1 1 1 0 0 0 2 3 4. That's upper triangular matrix. If the diagonal entries are non-zero, then we can assume the rest of the elements are zero. Rest of the elements are zero? No, you can't do that. Okay, we're gonna take this up now. I think this is a good trick because you will need tricks like these in the midterm. I can tell you that for sure. And I think this is a good trick that you should all know. Let me just take this down here. Take a screenshot, copy that. Extension. Oh, is that an upper triangular matrix? We're saying here, because we're saying here, the all diagonal entries are non-zero. That's the only reason why, but yeah, okay. Now, the way we're gonna solve this is, okay, we're going to write this as a, if the diagonal entries are all non-zero, prove that the column vector is linearly independent. Okay, we're gonna talk about it in the sense that something like this, right? If we have a matrix, I'm gonna draw a sample matrix here for you guys, M11, M12, all the way until M1n, 0, all the way to 0. This is going to be M22, all the way to 0. And let me write 0 here as well. And similar thing keeps continuing. What would I write here in the bottom right component? I want to see if people know what I will plan to write. So if this is M2n, M3n, what goes in the bottom right component? M and n, perfect. And the reason I asked that is we know it's an n by n matrix, so that's the only reason that it's the same letter. But I wanted to see if people were paying attention. Perfect. And we're going to write this over here as just a vector x with the length n. So we're going to say x1, x2, all the way till xn is equal to 0 vector. I'm just writing this for a second, and I want to ask actually people now, why have I written this? What do we need to now prove? Like if we've written it in this form, what is left to prove? What is this the same thing as we were talking before a minute ago, we were talking about this, something similar. What is left to prove? Linear combination of the columns is equal to 0, correct? All the xi are 0, yeah. So you need the, like this would be the same thing as writing m1. So this would be the same thing as saying mx1 m11 plus x2 m12 plus all the way till xn m and n is equal to 0. But if this is true, is equal to 0, but the way that all these columns would be linearly independent is if and only, so then we have linearly independent if and only if x1 equals to all the way till x equals all the way till xn is equal to 0. Okay, so that's why we're going to make use of this. And what we're going to sit down here is now, let's start with the bottom row first of all. So this is the trick I wanted people to pay attention to. Let's start with, so in this question like this, you want to pay attention to the smallest possible place to start. And in this case, it's going to be m and n multiplied by xn is equal to 0. Okay, you're given that. What must m and n or xn be in this case? Or you don't need to know the exact value, but what is 0? You're right. Well, what is 0? Xn is equal to 0. Perfect. Because m and n does not equal to 0, we're given that, right? We're saying that all the diagonal entries are non-zero. Therefore, xn is equal to 0. Okay, so we proved xn is 0. Now we have to prove everything before xn is equal to 0, right? We have to prove xn minus 1 is not equal to 0, and so on. And the way we're going to do this is now we're going to look at, so we've done the bottom row. Now we're going to look at the second bottom row. I haven't written it, but that will have the form So I'm gonna actually label this bottom row. And the second thing we're gonna label is second to the bottom row. And that will have the equation mn minus, so it'll be the second to last row. So it'll be mn minus 1, mn minus 1, multiplied by mn minus 1, n minus 1, xn minus 1, and it will be plus mn minus 1, n, xn minus 1. That's right, just n this time is equal to 0. Can everyone see why I've written this way, right? Because the first subscript in these situations is always the row number. And since we're in the second to last row, these will be the same. But the second element represents the column number, and we're having the one element here and one in the last column. So after we've written this, we make use of this. So this is the trick. Using xn is equal to 0, this is the same thing as mn minus 1, n minus 1, xn minus 1 is equal to 0. But now you've arrived at a case where you told me this before, that all the diagonal entries must be non-zero. This cannot equal to 0, right? We said this from before. Since this is true, then xn minus 1 has to be equal to 0. And that's the trick. We're going to keep going. And then from this point in the exam also, you can do this. After you've proved for 2 rows, you can say, like, using the same trick for all remaining rows, we see that x1 equals to x2 equals to all the way to xn is equal to 0, right? And so as wanted. Hence, all columns of M are linearly independent. That's it. Cool. I see we're on the hour mark. I'll ask everyone, we're going to take a break until 8:12. Scroll up for sure. And then we'll come back at 8:12 and solve the remaining questions. So I'll just say, and I also need that second to finalize the last 2 problems. So break until 8:12. And then we'll come back to solving problems. I'll leave this here. Actually, I can't leave this here the whole time. I'll take off the iPad in just a second. I need to import the rest of the slides, but I'll leave it for a second and I'll be back at 8:12. Okay, let's get back into it. Just give me 1 second. I need to stop sharing for 1 second, and then I'll share my screen once again. It's good to see so many people still here. We're going to now go into the second half of the second half of everything before reading week, pretty much. And let me just open this in Finder. Share. New document. Documents. Perfect. Let me share my screen again. Cool. And let me. So we stopped at linear independence. Didn't do basis, linear independence, linear independence. So we're at linear combinations now. Okay, so linear, oops, that's too zoomed in. Linear combination, it's something we've seen before. It's let me just, okay. So linear combinations, we just take our vectors in a set and we have some scalars around it, right? C1 to CK. And that's all that really is to the definition. Let's jump into a question here. Let me add a page, blank page, awesome. Here. There. Linear combination, that didn't work. Sample question, there it is. Okay, so we're gonna, in this question, suppose that there's an n by n matrix M, and it's composed of column vectors B1 to Bm. Prove that a vector V, a part of Rn, can be written as a linear combination of the column vectors if and only if there exists a vector X such that solves the equation that. Might seem a bit straightforward, trivial, and it's not difficult, so you won't be wrong. Just how would you go about proving that kind of thing? Okay, so we are given, so we need to show that a vector can be written like that. So we're going to first of all start off by writing this. So we're going to first suppose that, can I write it here? I'll start here and then I'll go down. Suppose V is a linear. So again, if and only if, so we have to go both directions. So first we're going to do, let me write this again. This direction. So we're going to suppose V can be written as a linear combination of B1 all the way to Bm. And that's the same thing as saying there exists x1 till xm such that x1 multiplied by b1 plus all the way to xm bm is equal to v, right? So I'm just rewriting the definition of scalar of linear combination. So we're assuming that, and we are going to actually, this direction is pretty that straightforward. So we can define a column vector. And what will the column vector? So, and I'm going to conclude then X satisfies, I'm not done yet, satisfies mx equals to v. And what will we write the X vector to be? What vector X would satisfy mx is equal to v? The column vector is perfect. X1, X2, all the way to Xn. or xm. Yeah, good correction. Right, we just use the coefficients of the linear combination that we specified here and put them into a vector, column vector, and mx multiplied by v would hold in that case. So pretty straightforward in that direction. And it's going to be pretty straightforward in the other direction too. So in the backwards direction, suppose there exists a vector x such that mx is equal to v. Suppose. And we want to prove eventually that v can be written as a linear combination of the column vectors. How do we do that? Well, we're going to now say, and let's say column vector x, let x is equal to, again, just x1, arbitrary elements for now, till xm. We haven't specified what correlation to have with v. We can use these elements. We can use these components, let's say, to form x1 b1 plus x2 b2. We're just going backwards in a sense. xm bm is equal to mx, right? We're just saying that our m in that case, so we got these from the column vectors of m. And that was given to us in the question, right? And we're making use of that. We have written x, a linear combination of the columns of m, and multiplied it by x. And we know that we're supposing, well, that and we know that, sorry, that this must be equal to v. And so because we suppose that in their question, so the vector v is a linear combination. So this was a pretty straightforward question. I couldn't find something too tough. Yeah, I'll go up in a second, of column vectors b1 all the way to bm. I'll zoom out now and you can take a look at the question. Cool. What are we going to jump into next? I'll leave it up for a second. Can you take a screenshot if you still need it? Cool. Yeah, question? No question. Okay. Solving systems of linear equations. We know how to do this, or we should know how to do this. If we don't, we'll go over it now. You know, we'll have a bunch of equations and we need to find x1 to xn values such that those equations hold true. What you may not know is a homogeneous system of equations is just where you're setting all the b1s to bm's equal to 0. And a solution, that's just telling you what the system means. Okay, so can you want to see the whole question again? I'll leave it up one more second. You take a screenshot. Cool. And so now what we're gonna, first of all, we're just gonna solve a system of linear equations. I know this is boring, we've seen this before. Some of us might not be so comfortable for it. So I just wanted to go over one example, a quick example rather, for this kind of question. So for this one, for part A, what we're gonna do is just put the matrices in matrix form. Sorry, the equations in a matrix form. So we know augmented matrix is, well, it's going to be 1 1 0 0 minus 1 1. We're going to have 0 1 2 1 3 1. We're going to have 1 0 minus 1 1 1 0. Everyone comfortable with how we went from this to this? Everyone comfortable with that? Cool. If someone's not, just please let me know. We're going to do some basic row operations on this. we're gonna do R3 minus R1. That's gonna give you 1, 1, 0, 0, minus 1, 0, 1, 2, 1, 3. You're gonna get 0, minus 1, minus 1, 1, 2, and then 1, 1, minus 1. Now to jump a few steps here, I'm going to do 2 row operations on the same one. You shouldn't do this in the exam, but just for the sake of time. And just in general, you're doing linear algebra. The reason I'm doing this question, I know it's pretty straightforward. You've probably seen this before. Make sure for the exam, you're 100% confident on solving a system of linear equations. It's linear algebra. I'll be surprised if there isn't a question like this, right? Solving the system of linear equations. Again, I'm not saying there is or isn't, but I would be comfortable with solving something like this and making sure you make no mistakes, because often people know how to solve them, but because they've not practiced enough, they tend to make mistakes in the exam. So make sure you've gotten that practice.
Very easy to make mistakes on.
For sure, yeah.
Especially if they're really big too.
Yeah, one small mistake will cost you like half the marks, and you don't want that. So make sure you don't do that. So here I'm doing row 1 minus row 2, but I'm also doing row 3 plus R2 just to jump one step here. But in the exam, please don't merge 2 steps in one. You will tend to make a mistake. 2, 1, 3, but just for the interest of time, 0, 1, 2, 5, and we'll be left with 0, 1, 0. And you can follow along with me and do this on your own and tell me if you get something, get the same thing. You should get the same thing if it's right. I believe I'm right. But just let me know. R1 plus 2, R3 we're going to do here. And at the same time, we're also going to do R2 minus 2, R3. And that will give you, that should give you R1 plus 2, R3 will be 1, 0, 0, 3. Wasn't x5 minus 5 in the first row? X5 minus 5 in the first row? No, it's just minus 1. No problem. So then we have 3, 6, and we're gonna get for R2 minus 2, R3, 0, 1, 0, minus 3, minus 7, 0, 0, 1, 2, 5, and our augmented column is 0, 1, 0. And someone tell me, do I need to, is this in RREF form? Yes, perfect.
Yes.
Perfect. Perfect. So we've done that. And now we were not, are we done? Basic and free variables. No, why aren't we done? Tell me why not. What do we need to do? Not in echelon form.
Find out the 2 other values, maybe.
What do you mean by that? Right, equations, it is in echelon form, not explicitly. We've not explicitly stated the set of solutions. Exactly, that's exactly what I was looking for. We haven't yet, what are the solutions, right? We haven't found our solutions yet. So that's what's left to do. We're saying, remember when we were defining this, we said that, so we have leading ones. And if you didn't follow along and solve it with me, I recommend like just take a screenshot from what we have and try to solve this system of linear equations on your own. See if you get the same solution, just so that you are practiced with solving system of linear equations. We see that we have leading ones in x1, x2, and x3. And so, and we have, and x2, x4, x5 are, what am I putting in the blank?
Free variables.
Perfect. Question about, again, just check your knowledge of the topics. I'm gonna say x1. There's another thing I wanted to hear, but x1, x2, x3, and x4, x5 are blank variables, and x2, 4, and x5 are blank variables. What goes in the first blank? Basic. What does that mean? I'm looking for a different word. if we are able to write, okay, dependent, which one's dependent? Perfect, perfect, perfect. That's exactly what I was looking for. We need to also know that these are dependent variables, right? Think about it in this way. We need x4 and x5 to be able to define x1, and x4 and x5 are just independent. Make sure you know this. It can be tested because we need to write x1. So solution set is x1 is equal to minus 3x4 plus, sorry, minus 6x5. x2 is equal to 3x4 plus 7x5 plus 1. And x3 is equal to minus 2x4 minus 5x x5. Perfect. And then for any perfect. I want to check something. While everyone just takes that in, I want to check just one thing. Participants. Alex, would you mind doing me a favor? Could you message Katrina and ask her to get us a Discord invite link for our community server for AMAX?
Absolutely, yeah.
Yeah, I think it'd be a good idea. We can just share the notes in there for the people so that you can also join the community server. So just message while we continue on. Perfect. And for the second question, remember we weren't done just quite yet. We had to also, this part, we have to determine all possibilities for a solution set of homogeneous system of equations, of two equations and two unknowns that has a solution to that. Okay. Okay. First of all, I don't know how to spell this thing. Homogeneous system. What must they always be? You should know this. 0. That is what it means, that the equations are equal to 0. But what about the solution set for a homogeneous system of equations? Perfect. I think, is that the right Discord? Let me just check. Yep, it is. So please join the, so Armand there shared the link for our AMAX community server. Please join it there. I'll try my best to get the solutions shared there. Again, I just have to confirm that with the prof. So as soon as he replies, I'll get that shared out. Make sure you join the community server. We'll have a lot more events and stuff coming up in there and review seminars. So be on the lookout for that. So just join the server and I'll share the stuff in there. Have a trivial solution. Perfect. That's exactly what I was looking for. Homogeneous system of equations must always have the solution are always consistent is what I wanted to say. And have solution x1 is equal to xn is equal to 0. In this case, we are perfect. Thank you, Alankrit, as well for that. Thank you so much. Yes, please, guys, everyone check the stuff in the chat. We're have some big plans for this year, so make sure to be in sync. Okay, so they must always have these solutions. We have two equations. We have two equations, so we must have, my handwriting's terrible, have x1 is equal to 0 and x2 is equal to 0 as a solution, right? Okay, first system of linear equations. You have three possibilities, right? 1, no solutions. 2, 1 solution. What's 3?
Infinite solutions.
Can you have this? Can you have 2 solutions? No, perfect, good, people know. So if we have a homogeneous system of equations and we're saying that this is a solution and the question is saying that this is also a solution, right? So what do we know about our homogeneous system of equations, then we must have it, exactly. And given x1 equal to 1, x2 equal to 5 solution, hence must have infinite solutions. And that's it. Questions about that? I'll just screen to that. Admit this last person. Cool. With that being said, let's jump on to, I know we're just 30 minutes to go and we have 2 sets of questions. Why no 2 solutions? It's just not like you can only have no solutions, 1 solution, or infinite solutions for all system of linear equations. So it's just not a
Yeah.
It's just a definition of linear system.
Yeah.
One question about this.
Go ahead.
So why is it infinite and not 1 again? Just to be clear, just want to know.
What do you mean? Infinite
I
amount?
mean, sorry, why is it infinite solutions and not 1 solution?
Yeah,
Is
because
that-
we have a system of homogeneous equations. We know that that homogeneous system of equations must have 0, 0 as a solution. We're also
Okay.
given the question that we have this 1, 5 solution.
Oh, I see. Okay, sorry, I didn't see that one. Okay, thanks.
No
Okay, I
problem,
see.
no problem.
If
Okay.
you want to think about this geometrically, linear solutions to a system of linear equations usually always represent some sort of like flat objects. So a line, a plane, a hyperplane, etc. And those can only intersect each other either at 1 point or infinitely many points. Like you can't, for example, if you have 2 planes, you can't have 2 planes intersect at only 2 points. They either intersect nowhere or they intersect infinitely or at infinitely many points.
Yep, and there's the question. Just please screenshot it so I can move on to the basis stuff. So for the basis and dimension, we know we have this definition here. Basis is just a linear independent set for spanning, is a linearly independent spanning set for V. So can you go for 2 seconds? I will just 1 second. So 1, linearly independent, and 2, spanning set. So those 2 things are important. And then just before I go, number of vectors in a basis is called the dimension. We know that. Okay, I'll just go up and I'll give you guys a little bit longer.
It's important to note actually that is well defined. So someone might ask the question, well, what if you have 1 basis with 2
Higher?
vectors and 1 base with 3? Well, the answer is that's not possible. All bases must have the same amount of vectors.
Yeah, got it. Okay, perfect. 1 second. Perfect. And so we're gonna now jump into dimension. We already did. Okay. So dimension and basis, we've defined it. Perfect. Now let's start with this one. We're given a set S. I'll just bring this down actually. And we want to find the basis. So we're given find the basis for span of that. Okay, so this is the relatively easier question. How may we go about solving this one? Call it A. Any ideas? Linear systems. What do you mean? What do you mean by linear systems? You might be right. Check if the vectors are independent. You're right. How do we do that? If there are, then it's basis. Okay, you're right. But how do we do it? Express them as a combination. Perfect. Let's do that. And let's do it first. I'll write that part just for everyone to see. 1, 2, 1. We're gonna do plus x2 minus 1, 2 minus 1 minus 1, 2 plus x3, 2 6 minus 2, and plus x4. What am I gonna write here? Express them as a combination and write exactly equate them to 0. Now simply we're gonna put this in a matrix. First of all, just before we get into that, before we get into that, just by looking at this set, I want to see if people are paying attention. Is there any vector you can automatically eliminate from being in the basis? Just by looking
We
at
can
it?
remove the predominant vector, second one.
The second one, right? So we know that this one's kind of useless already. Before we go into properly showing it, we can see that this one's useless because it's just a negation of the first one. First or second, yeah, of course. You can remove the first or second in that case. So we're gonna now show it more formally. So again, like we did before, 1, 2, 1, -1, 2, -1, -1, 2, 6, -2, 1, 1, 3, and we're going to have an augmented column of 0, 0, 0. There's only one row reduction step, so I'm just gonna actually there's two, but I'll just do what they will do. R2 minus 2 R1 and R3 minus R1. That will give us 1 minus 1 2 1 0 0 0 0, and again you can verify this. Minus 1 2 0 0 0, and the final matrix you would get in this case is 1 minus 1 2 1 0 0 0 0 1 0 negative a half 0 zeros in the augmented column. Perfect. Now that we've gone here, why we let this linear independence? Are we trying to solve for linear independence? Yes. So because we're trying to solve for linear independence, we write the linear equation combination to equate to 0 because we want to show that x1 to we want to aren't we trying to solve for linear independence? Yeah, we need to see which columns will end up being redundant. In fact, like you don't really even need this last column because you'll see that we don't actually do anything with this last column over here because based on this, the steps are write in matrix, right? 2 RREF, 3 select columns with leading ones. And actually you're right, in this case we don't really need the zeros column because we don't actually end up using it. And so if we've done step 1, we've done step 2. So what is our basis vectors? Which are the span basis vectors? Use what we wrote in step 3. 2 and 4.
Is it 2, 2, 3, and 4, I believe?
No. For all, it's not 2 and 4, it's not 2, 3, and 4. Let's see if someone else is able to get it. Can you add 2 times second row to R1? 2 times second row to R1. Why would we do that though? 1 and 3, 1 and 3. Yeah, you could do it, but it doesn't. This is in our REF. We don't need to do anything after that. And yes, we need 1 and 3. Question as a test for you guys. Are we done? Why is it 1 and 3? Because the steps, like we said over here, we need to select the columns with leading ones. This column has a leading one, and this column has a leading one. Leading one means, I didn't write this properly. This is supposed to be a 0. How bad about that? This is supposed to be a 0 there, and this is supposed to be 2. My bad. I didn't write the last step properly. I meant 2 and 4 of the initial vectors in S. Oh, okay, okay. Doesn't have 0. My bad. I didn't write that properly. But based on this, did you make the last row all zeros using elementary row operations? Yes, I did. You can verify that by what did I do in the last step? From here to here, all we did was adding 2 times the second row to the last row. Now, can anyone tell me what the basis vectors are? Are we done? You didn't write them down? Sorry about that. So R2 minus, no, sorry, R2 So we're gonna do two things, R2 minus, sorry, R3 minus 2R2, and we're gonna do R2 divided by 2. How did you get the basis? Okay, first of all, so this one's confusing people. Shouldn't the second vector be 0, 1, 0? Sure, but okay, is this right now?
How did you get the basis? Michelle, all we did was we looked at the set and we saw, okay, which vector can we remove so that our set becomes linearly independent? And we know that all bases for R3 are size 3. So once we know that we have a linearly independent set of size 3, we know we have a basis.
Yeah, just the thing, guys. I didn't say this is right. I didn't say this basis is right, and no one was able to identify that it's whether it is or not. So don't take my word for it. Tell me if it's right or wrong. And that should hint it towards saying that that is not right. What I've written right here is not right. I wanted to see if people are understanding. You have to check if it's a spanning set. Wrong. I got 1, 1, 0. I believe it is incorrect. This is incorrect. I think this RREF part is fine. But even if it's not, assume this is the final RREF matrix you get. The important point is from getting from here to here. But okay, maybe my row reductions are wrong. But regardless, assume this is your RREF matrix. What would your basis be if that was your RREF matrix? 0, 0, 1. No. Isn't the basis 1 to 1 perfect? Thank you so much. Finally, someone got it. Exactly. Arashi as well said it there, and we can solve basic exact. Perfect. So that was just a trick. We were just testing it. So it is right that we first saw that this column and this column has a leading one, but select from original set, not RREF matrix, right? So be careful about that, guys. And so your final basis should be 1, 2, 1 and 2, 6, 2. I've seen this mistake so many times when marking. So please make sure you don't make this mistake. Select it from the original set, not the row reduced matrix. Couldn't you use the row operations to get into reduced echelon form? We have gotten it into row echelon form. Could you zoom out? Of course I can. Okay. Please take a screenshot if you haven't already. What do I have left after this? Linear transformation. I think it's important I cover a question for null space and range, which means the same thing as kernel and image. But there is one more basis, and I see people struggle with basis and dimension more. So I'll try my best to quickly finish this linear transformation question. I'm not going over linear transformations. I know that's pretty basic, but again, it just means the two things, right? The addition and scalar multiplication. Null space is equivalent to what was said in lecture as kernel, and the range is equivalent to what was said in lecture as image. Okay, so these are just two interchangeable terms. I'm going to go over this last question. I know we're a little bit tight on time, but I do think it's important we go over null space and range before we stop the review seminar. Just take a second to read the question and think about how we may go about solving this. Could you zoom out again? Okay. I'll go back to this. Please take a screenshot if you haven't already. Cool. This question. Give you 1 or 2 minutes to go over this, just so that we have enough time to go back to that independent or basis question, sorry. Could you scroll up to the definitions, of course? It is linear map. That is correct. How are we going to show that? Okay, so and we're going to show that by let F and G be a part of. What am I going to take two elements to be a part of? What is the domain in this case that we're working on? Am I going to take two elements from here? C. C from -1 to 1. By definition, yes, that's what we have to prove. But I'm saying don't take two elements from here because we don't know that just yet. We want to take two elements from here. So we're going to take F and G a part of continuous functions from -1 to 1. And I know Parker loves his going back to like integration questions and functions questions, polynomials, all that stuff. So that's the reason I picked an example just like that. We need to show, T of F plus G of X is equal to T of F X plus T of G X, right? That's the goal. So we're going to start from our left-hand side and show that it's equal to the right-hand side. So our left-hand side is T of F plus G multiplied by X. So that is going to be the same thing as, how can we rewrite this? We were given what the transformation is, right? So we're going to rewrite this in the form of, right? So we need to write the original, so it's saying take the function, write the original function in terms of X. So we're going to say F plus G in terms of X. And like I said, like he loves making these kind of questions where you have to use a topic from a different course and apply it to linear algebra. And so I think it's important that you understand why I went from here to here. Is this right? Is this equivalent, right? Am I missing something? No.
Your
No.
T of F plus GX, it should be F plus GX minus F plus G0.
So we need to add that 0 here. And that will give us that. Now, how can I split this up? We know that this is the same thing as F of X plus G of X minus F of 0 minus G of 0. And then this is the same thing as F of X minus F of 0, just remove interchanging these terms, X minus G of 0, and that's the same thing as T of F of X plus T of G of X. And you do the same thing for multiplication, and that part should be pretty straightforward, so I'll just speed through that quickly. Let C be a part of reals, then T of CFX is equal to CF of X minus CF of 0 is equal to CFX minus CF 0, which is equal to C multiplied by the whole thing, F of X minus F of 0, which is equal to C T of F of X. And that's what we needed there. The reason I'm bringing this is, again, you're not going to get a very simple prove something's linear transformation. It's a midterm. It's, you know, first year of university. You're not going to get a very simple show linear transformation. The way it gets spiced up is when they introduce a different set of sets that you're working over. So that's the reason we're working like this. So we've shown it's a linear map. Now we need to determine its null space and range. So let's start off by null space or kernel. So let's say kernel. So we need to show that it's null space. Was there?
A little bit, yeah.
I think someone's not on mute. Please mute yourself. So we want to show that its null space is equal to something. So T is, suppose that F is X is a constant function. Okay. What do people think the null space for this would be? I'm going to write it actually, or the kernel. Kernel is equal to kernel of the transformation is equal to a set, right? F a part of, so we know that it must be elements from the domain, but what's condition must be satisfied? What must be true about F for it to be in the,
AX equals to 0, a times x equals to 0.
what's A?
Oh,
Fx is equal to 0? I'm looking for a condition to put here. What do I put here? F of 0 is equal to 0. What does this mean? Constant functions. F of x must be just equal to any arbitrary constant. F of x, and we'll show why this is true. So what we'll say is let f be a part of curve of t. Therefore, f, so t of f of x must be equal to what? Because it's a part of the kernel? 0. But that's also supposed to be equal to f of x minus f of 0, right? And the only way this is equal to 0 is if f of x, am I saying this right? T of f of x is equal to 0. We need f of x to equal to f of 0. So we actually need x to equal to f of 0. Does that make sense? So let me just add that condition. So that's our null space. Should not f of x equals 0 already satisfy it instead of only constant functions? If you had yeah, I get what you're saying. Well, because that's also just equal to 0, right? So yeah, that would be the same thing. Fair. That's a good point as well. But that's just the general structure for our kernel. Let's quickly, I know we're just 4 minutes to go. Just quickly talk about the range or image. We need to find the image of t, which we're going to say is equal to, which has to equal to the w, right? So let f be a part of w, right? So we want to find a set that we can write the whole of the range as. So if we're saying let f be a part of w, therefore f of 0 is equal to 0, then t of f of x is equal to f of x minus f of 0, which is equal to f of x. Therefore, f of x is a part of image of t. There isn't really anything we're proving here. Just need to state that this holds. And now we're going to say, now let. So here we've shown if f is a part of w, then f is a part of the image, right? Now we're going to say, let f of x be a part of the image of t, and therefore f is equal to t of g for some g, a part of the domain, which is continuous functions from -1 to 1, right? That's all we mean by the range or the image. Then f of 0 is equal to t of g of 0 is equal to g of 0 minus g of 0, which is equal to 0. And this is true. Therefore, f is a part of w. And the reason we've done this proof is now because we're able to conclude what am I going to write here? What condition must be true for every continuous function from -1 to 1 to be in the range? What do I write there?
F naught equals not 0, and the F is in this range.
Say the first part again.
F0 is equal to 0.
Perfect. That's all we need. And that's it. That's all we need to know for that proof. That leaves us right on the hour. I'll leave you guys with one extra bonus question for you to practice. You might not be able to easily prove this. Actually, again, so people are free to leave. I wanted to go over this one just so you're fully prepared for the midterm. I don't want people to not have the answer. So you're welcome to leave if you are tight on time or whatever. But I do want to just quickly go over this for everyone else as well. It won't take that long, but again, I don't want to keep people beyond the time. So if you need to leave, please feel free to head out. For everyone else, yikes, I've ruined that. Eesh. What am I doing? For everyone else, for part in this question, just read it very quickly and I'll just go over the quick solution for this very fast and then we can head out. How many people do we still have here? 119, that's great to see. Okay, so just read over this question quickly and then we'll go over the solution. I know people are weak on or not as comfortable with the basis and dimension stuff, so I want to go over one more quick question and then we'll head off from there. So for the first part, we need to prove that V is a subspace of R2, and we're saying A is just equal to that. So first, has everyone gotten a chance to read that question? Are these questions similar to the level of the midterm? I can't say. I don't know. To be honest, I really don't know. I can't say, but like, yeah.
Yeah, you can never really know like what's gonna be on the midterm until you take it. So it's like we can't really confirm. Especially I don't know if Sauhaard's TAing the course, but I'm not TAing the course, so I don't even know. I don't know like exactly, like I haven't seen any like practice tests or anything, so I don't have any hints about like what could possibly be on the midterm.
No, I am a TA for the course. I can't say whether or not I've seen the midterm, but there was no practice midterm, so if no one has seen that, but yeah, just don't like I've tried to include harder questions, but obviously it is a midterm, so it might not be the exact. Okay, anyways, everyone got a chance to read that question? So in V, AX equals 5X must hold. So in this question, do we assume that the subset is truly implied truly subset? Where does it say prove the subset of V? Prove that the subset V is a subset. It won't change your answer. So we have A is equal to this, and we need to consider the set V like this. And we want to show that V is a subspace of R2. You might not be able to fully solve this question just yet. I will just show you this part. I think is we need part A for part B, but if you don't understand part A, that's okay. So this must hold in part in the set V, and this is the same thing as AX minus 5X is equal to 0, right? And this is the same thing as A minus 5 blank X is equal to 0. What do I put in the blank? What do I put here?
1, 1, 1, 1.
Which is called, you're right, but what is it called? Not 1, 1, 1. It is the identity, but identity, careful, is equal to. 1 0 0 1, not 1 1 1 1. But yeah, that part's right. Now, once you move further in this course, I don't know if this has been covered already, but what this tells you is V is equal to X. I'm just writing V again. And rather, if I rewrite let, this is the same thing as saying so what does this tell me about V? I don't know if people would know this. I don't think it's been covered yet, but this tells us it's okay if you don't know this for the midterm. Again, don't get like stressed if you don't know this. Null space of R2. And you're going to find out null space equal R. Again, you don't need to know this for the midterm, I think. But the reason I've just done it is so that you don't think about how you do part A. Again, don't worry about part A. The reason I brought this question is because I want to do part B. We want to find a basis for V. And to find a basis for V, we need to use what we did in part A. Are always subspaces. I don't know what the question was. Okay, from part A, so now we need to find a basis of V. From A, we know A minus 5i x is equal to 0, right? We know that. I'm going to give you a hint that you need a matrix here. What matrix can I form? To find a basis, right? We need to find a matrix and row reducer, right? Like we said up here. Oh, where was it? We said it somewhere.
In part A.
Sorry?
In that question, in the same question.
In part A?
I mean, in the span, in defining the basis for the span.
I don't know. Regardless, anyway. The important part is what matrix can I row reduce? I'll give you a hint, we need a matrix, but like if you were given this question, okay, ignore what we did in part A, but you might have been given, this holds true. Or actually, let's say we know V is equal to the set. Someone said it already, perfect, but X is a part of R squared. So assume this is where you got the start question given. If you're confused about what we did in part A, just assume this was your question. Find. So let's say this is the question. Assume find basis for V. So if you were given this and you want to find a basis for V, we are given A. Yep. So to solve one, find A minus 5i as a matrix, which is going to be, we just take A, which was, what was it in the question? 4 1 3 2 4 1 3 2 minus 5 of the identity, which is 1 0 0 1, which is going to give you 4 1 3 2 minus 5 0 0 5, which is also equal to minus 1 0 1 3 minus 3. Okay, and now 2 RREF. I said this above, but I'm just going to write it again. So now we have 1 minus 1 1 3 minus 3, and that is going to row reduce to let's do R2 plus 3R1, and that is going to give you minus 1 1 0 0. And that can be just do minus R1 to give you 1 minus 1 0 0. And so which columns have leading ones?
The first column.
Yeah. leading one, which is in fact the first column. Therefore, basis. So what's our basis?
4, 3.
4, 3. You're right. But just
Yeah,
in
and just start, yeah, -130.
not quite. So actually, in this case, you don't actually need this method, this part just here. So we needed to do this until here, REF. But what we need to do now was, therefore, and. Okay. We found this. We knew that this was equal to 0, right? We knew that from the beginning that this was equal to 0. So if I just wrote, let me add a new page just to know, crowd out the place. So is this the same thing? Is this right, first of all? Is this right?
Yeah, because the condition is already given.
Yeah, so we already said in the question that we're equating it to 0. So if we're equating it to 0, we can add the augmented column 0, 0. And so what can we say the relationship between x1 and x2 is? Say this is x1, this is x2.
They are equal to each other.
Yes, so x1 must be equal to x2. And this is our solution for the basis. So in fact, our basis is, let's say basis of V is equal to a set of vectors x such that x equals x1, x2, such that x1 is equal to x2, right? Which is the same thing as saying, so x is equal to x1, x2. But since this is true, how can I rewrite this? You're right, 1, 1, but how do we get there?
We set x1 and x2 to be t and
Sure.
take out t as its scalar.
Perfect. So it's t multiplied by 1, 1. So in fact, our basis of B and that's it. The reason is so we saw 1, 1. Can 1, 1 be linearly dependent?
No, since it's only vector, it's one set of one vector, the set is never linearly dependent since it's non-zero.
Exactly. So we have found the basis. So dimension of V is equal to 1. And that's the solution to that problem. Perfect. So that is all for today. I'll give everyone just a chance to screenshot this. Can you explain again why V is in the null space of R2 again? It's not a null space of R2. We said that, did we say that actually? One sec. We just showed that V is a null space and any null space is a subspace of R2. That's what I said. But again, don't confuse yourself too much about that. You don't need to know that just yet. What is the question? That's the question. Okay. Can you show me the entire page? I'll do my best. Entire page is in this page. That's the best way. I can let me try to see what this does. That doesn't help. Scroll out more. I'll hold it. It doesn't stay like that, so I'll just hold it like zoomed out like that, so you can take a screenshot. But yeah, that's all I can do, unfortunately. Cool.
One question.
Yeah, of course.
In finding the basis of a set, I mean the set of vectors that span the space, why is it always true that the column vectors containing the leading zeros are the dependent ones?
It's the leading ones that are the lead. And it's because when you're doing the row reduction, you're finding the vectors which can be, or you're eliminating the vectors rather, that can be written as a linear combination of other vectors in the spanning set. So if you're getting a column where the leading one is not there, it means it got removed by another column, another vector that eliminated the need for that vector. So that's why we only take the leading ones. Can you explain one more time how we got 1, 1? We got 1, 1 because we row reduced it and we got to this matrix, which was the first row was supposed to equal to 0. So we had x1 is equal x1 minus x2 is equal to 0. Therefore, x1 is equal to x2. And so any vector in the V must be any x a part of V must be in form T multiplied by 1. And that's why 1 is the vector. Okay. If no more questions, make sure you guys join that Discord link that we shared above. I'll try my best also to get it shared through Quarkus, but I'll have to ask Parker for that. Thank you everyone for coming. I appreciate everyone who stayed behind. I wish you all the best. I had this written somewhere, but yeah, good luck on the midterm and good luck on the midterm. Yeah. And thank you for coming, guys.
Best of luck, everyone.
No problem.
Excuse me.
Yeah. What's up?
Yeah, can you show the question, a question about the kernel and image, please?
Kernel and image, this one?
Yeah, the one below, just a little lower, just so I can see the entire.
There you go.
Thank you.
No problem.
Sauhaard, can you like check your email after the session?
I will do.
Yeah,
Quick, can you zoom in a bit more? I don't think I can get just do it like in like half, like just big enough for, like
So-
it covers one half of the
Do you
page.
need the
and-
question?
Huh?
Do you need the question or do you want the answer only?
Yeah, I need the question, sure.
Okay, so take that.
Okay, yeah, I got it.
You can take
Just a little bit up. I just want to see like just everything except for like I want to see like the entire thing with just yeah. Okay, got it. Thanks.
no problem. So for those people asking, I'll post the notes immediately in our Discord, community Discord. I'll do my best to get it posted on Quarkus as well, but I'll post them on the Discord. The recording, it just takes some time to process and stuff. So if it's not up by tonight, it should be in there by tomorrow in the Discord. And again, I'll ask Parker if I can share it on Quarkus as well. But yeah, thank you all for coming. No problem.
Excuse me. Do you mind going through the question of the one more time of the one where it has mx equals v, that one?
Mx equals v. Let's go to that one.
If and only if one.
Yeah, of course. This one.
Yeah.
Is there a particular direction or would you like me to go through both?
Both preferably.
Sure, of course. So for the first half, so first we're just supposing v can, so we're supposing this part, so v can be written as a linear combination of b1 to bm, and we want to prove that x, so and there exists a vector, and so we want to prove that there exists a vector x such that this holds. So we suppose the first part, v can be written as a linear combination of the column vectors, and we said the column vectors are b1 to bm. So we're supposing v can be written as a linear combination of b1 to bm. So if that is true, that there must exist a set of x1 to xm such that x1 b1 plus xm b2 x2 b2 plus all the way to xm bm is equal to v, because v can be written as a linear combination of those b1 to bms. Conrad, the recording will be in the Discord as well. I'll share like a link to that, and then if it's not there by tonight, it'll be there by tomorrow, and I'll otherwise also get it shared through Parker if that's possible. Okay, but I do know that Parker doesn't reply to emails that well on weekends, so it might just have to be in the Discord. So make sure you do join that Discord. So now after we've assumed we've gotten to this part, we just take all those x1s and put them in a column vector x, and because we're doing that, we know that x multiplied by, and m is is like B1, Bm. The columns are those vectors B1 to Bm. So that's why that part holds true. Now going the other way, we need to suppose that there exists a vector x such that this holds, and we want to prove that V can be written as the linear combination of the column vectors B1 to Bm. Okay, so we're assuming there exists an x such that's true. So if we're assuming that there exists an x, let's call the x this x. So x1 to xm, we're just arbitrary elements for now. After that, we can use these x1 to xm's to multiply by m, because we know that this is true. We know that there exists an x such that when we multiply by m, we get v. So let's multiply the x with the column vectors of m, which are b1, 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 b2, b all the way to bm. So you write that linear combination, and we know that that must be equal to mx, and that's also equal to v because we're assuming that in the first part. So we have written v as a linear combination of b1 to bm, and we have shown that v is writable as a linear combination from b1 to bm.
Oh, okay. I
Does that
see.
make more sense?
Yeah. Okay. Thank you.
No problem.
Hi, bit of a quick question. So can you go to again, back to the question, like I need for the last question about like, I have a question about like, how do you prove the image for the last question again, just like the image? So, okay, I get the part of like, you have to find like image T is like equals W, and that F is like exists within W, but the question is like for the part about with the F equals TG for some G that exists within -1 and 2 in the interval. Just a quick question: how did you get like F0 equals 0 like for the image again? Like that's the question. How does like how did you get like F like the image lies in the range of T if F0 equals 0?
From this
Just
part,
one.
because we wrote f0 as tg0, right?
Yeah.
And that gives you g0 minus g0, which is equal to 0. So as a conclusion, we got from here to here, right?
Yeah, so F0 equals 0. Oh yeah, I got that. Okay.
Yeah.
So okay, I see. So okay, just so okay, so that's so TG is like equals to like the transformation of G G of X minus G of 0, right? That's the transformation.
Exactly.
Okay, all right, okay, I see. Okay, thanks.
No problem.
Also, can you go back to the bases and the first, like, not the question, the new one, but like the old one for bases and dimension?
This one. This
Yeah,
one.
like for base, just like the normal question, like, it's not like the new one, yeah.
I think it's gone down here. Yeah, this one.
Okay. Okay. Okay, so a quick question. So when do you have to do a select from the original set from the not from the RREF matrix? Like for the one we did before, like the one with the AX equals to 5x or something, we just had to use like a 1, 0 or something, like just solve it with with normally, like with equivalency, like to find the dimension of it, like in R2. But when do you use like the original set?
When you are given a set of vectors, like we were given here a set of vectors, right? Like
Okay.
in that case, we couldn't have selected like in that case for the one you were talking about before, when we couldn't have selected like the original vector from the first column because there was no set of vectors that we were working on initially, right?
Okay.
Here we had 4 vectors over here, and we saw that the pivots are in the first and third column.
Yeah.
So you always just go back to the original. In this case, when you have 4 vectors here, you always go back to the original.
Okay, all right. And okay, so and the basis is like the only ones that have the leading ones in it, right? Like,
Correct.
and for solving like the ones like for like sorry, for like dimensions or something like that, do you also use the ones that have when do you use the ones for free variables, like the columns with free variables or something?
Uh, that's for the that's something different. You're talking about basis and null space when you have, so you're talking about null space and image, and the image will be the ones that have a leading one, and the null space are the ones that don't have a leading one. So that you count
okay.
numbers for those.
All right, okay, I see. Okay, thanks. Okay, thank you.
No problem. When they ask to calculate for the kernel or image of T, we're supposed to find a set for that, right? Yeah, exactly. You just need to find what the set can be defined as for the image and kernel. Cool, so I'll stop the recording there.